Okay, so we are still about this optimization for generalized linear model, if you recall where we are. So we basically talk about the generalized linear model under exponential family, right? So like we always have, there is a random structure. I always like to start with this stratification of our model. We have a random structure, which is about our each response yi independently following some exponential family with a location parameter specific to I, theta I, and the common scale parameter phi. And for the systematic structure, it is where we want to link our response to our covariates. So we want to link the response yi to the covariates of the ith observation. We call that xi. So I'm trying to zoom in to give you a better quality. So for this one, we actually want to link the expectation of yi, which we call mu I. We want to link it with the covariates, xi transpose beta. And beta will give us the effects of the covariates. So if we are specifically interested in covariate J, right, xi, we denote it as a p-dimensional vector, including one intercept and p-1 covariates. If we are interested in a specific covariate, we look for its coefficient in this beta. So therefore, the question becomes, how do we estimate this beta? But before we go there are many things we need to link together, all related to the location parameter. So if we are under the canonical link function, we have this relationship specified as theta I equals to this linear predictor eta I. And also for this EYI, expectation of YI, we give it the notation mu I. So we specify this relationship G of mu I equals XI transpose beta. So this is how we can link the location parameter to this common beta. And you can see that on the left-hand side, theta I is specific to observation I. On the right-hand side, beta is the common beta for all observations. So we're not assuming that the effects of covariates are specific to the ith observation. And the specificity only comes from the xi, only comes from the specific covariates. The covariates are specific, but the effect beta is common. This is very important to know. So when we want to estimate beta, it becomes an optimization problem. We want to minimize the log likelihood written in beta, and beta is a p-dimensional vector. So it becomes an optimization problem. And because in this case, the log likelihood is not a very easy form like in the linear model case. In the linear model case, we could just take the gradient against beta, set the gradient to 0, and solve for beta. That was easy. But in this case, we cannot easily solve that gradient to 0 question. Therefore, we use an iterative approach. And this iterative approach started from Newton-Raphson. In Newton-Raphson, we tried to approximate the gradient of beta by Taylor expansion. So we go to the second derivative, the Hessian matrix of the log likelihood. So we set that approximate gradient to 0 for the update. And in Fisher scoring, what we did is that we replaced the Hessian matrix by the expectation of the Hessian matrix. And expectations taken over Y1 to Yn, the n random responses, because the Hessian matrix is the second derivative of the log likelihood, and it involves Y1 to Yn. So taking the expectation for Y1 to Yn is a way to simplify our calculation. So in short, For Fisher scoring applied to this problem, we actually have this update. Fisher scoring. And if we are in the, I'll just use the notation more consistent with the notes, in the kth iteration. Suppose that our current value, current parameter value is denoted by beta k. Okay, then the question is, how do we find the next beta value, beta k plus 1? And the update can be written as beta k plus 1 is beta k plus the inverse of the Fisher information matrix at beta k. We take the inverse of that times the score function. Score function is the gradient of the log likelihood at beta k. So I want to draw your attention to the score function because for a general class of tests for beta, we can call them score tests, which are constructed based on the score of the gradient of the log likelihood. Even though we haven't talked about them specifically, if you recall, to test for beta equals 0, we gave you multiple options: the wall test, the ANOVA, the likelihood ratio test. So the difference is that wall test focuses on beta, and we focus on using beta hat, while the likelihood ratio test and ANOVA are more in the global sense, in which we are interested in assessing the difference on the likelihood when beta is set to 0 versus not 0. That's the likelihood ratio test, while the ANOVA focuses on the variance decomposition, whether the variance explained by covariance is 0. So even though they come from different perspectives, but they become equivalent in their goal, whether with our covariates have effects or not. So the wall test focuses on the beta as the coefficient, likelihood ratio test focuses on the likelihood, while the variance decomposition or ANOVA test focuses on the variance decomposition. So later, I hope I can add some new material to the course by saying that we can have score test as a general way for testing beta. So score function is important. And Fisher information is the expectation of the negative Hessian. All right. So if you recall our detailed derivation, last lecture on Monday, what we did is that we tried to derive the score function, the score, and also the Fisher information. So we used the multivariate calculus to help us derive both. And the form we actually get can be written in a simple and elegant way. That is, the Fisher information can be written as X transpose a weight matrix with the kth iteration parameters, X inverse, X transpose WK, and this is a vector notation, Y minus mu, d eta, d mu. This is a whole notation at the kth values. So just as a reminder, let me try to tell you what each notation means. So one is that this WK, one is this vector, okay? So where W, if we just drop this kth index for the kth value, it's a diagonal matrix where the first entry is 1 over the variance of Y1, the response, times the square of G prime, gradient of G, the length function, the derivative of G at the length function of the length function at mu1 square. This is the first diagonal entry. And we have 1 over variance of Yn G prime mu n square. And the other entries are 0. Okay, yeah, I think the resolution today somehow is not very good. Let me try to adjust it. Maybe I can. Okay. So this is the W matrix, and this vector y minus mu d eta d mu. This is a row vector, and we can write it out as y1 minus mu1 g prime mu1 yn minus mu n g prime mu n. Okay, so if you are familiar with Taylor expansion, which we can use for the so-called delta method, in which we can derive the mean and the variance of a transform random variable. So if we transform yi to gyi, then what's the mean of gyi? What's the variance of gyi? We can actually find that it can be approximate in this way. So this is like the Taylor expansion form or delta method form. And in fact, this is the intuition we get out of the update. So what can happen from this line? Okay, so we have the Fisher scoring update as this. If I mark it as star, then from star, we can multiply this X transpose WKX on both sides, and you can see something interesting would happen. Multiply X transpose WKX on both sides. So if we do this, then we will get X transpose WKX beta K plus 1 equals X transpose WK X beta K, right? And plus, we can cancel out this inverse X transpose WK, this vector y minus mu d eta d mu, together we label index K for the iteration. And then you can see that for the right two terms, we can combine them because they both have X transpose WK in front of them. So we get X transpose WK, combine the terms, X beta K plus Y minus mu d eta d mu K. That's it. And then you see what can happen is that if I denote this term by a notation, if I denote this term, call it a notation ZK, which is itself a n-dimensional vector. So this is m by 1. If I denote that, then I can find that my update can be further simplified just like a weighted least square form. So then you can see that this will give me beta K plus 1 becomes X transpose WK X inverse X transpose WK ZK. So this is like weighted least square, which we introduced in our last lecture. It's just that in this weighted least square solution, the response is not Y, but the response is ZK. ZK is what we define as this form. Okay, and we actually give this ZK a name in the generalized linear model, this iterative framework. We call it working dependent variable. So the reason we call it here is that this is the thing we're working on, we're working with. So it's a working variable. And it's a dependent variable just as the y, just as in the weighted least square, the response. We call the y dependent variable, and we call the covariance independent variable, right? That's another set of terminology you might have heard of. But here the dependent variable is the working version, because every iteration we will update it, right? So it will not stay the same, it will be updated. So that's why it carries the index for the iteration k. Okay, so the nice thing here is that we change each iteration to solve a weighted least square. And because the weights are also updated, every time once with k changes, wk will change accordingly, because wk is the variance of each yi will involve parameter values, and this derivative at mu I also involve parameter values. So that's why as long as we update our parameter values, the weight matrix will be updated. So that's why we call reweighted. So this whole thing is called iteratively reweighted least square. So that's why the short name for this algorithm is called IRLS. And it's still the one used in the GLM function in R. The good thing about this is that we just need to have the algorithm for weighted least square. If we have the way to solve weighted least square, then we can apply it iteratively in our iteration. So that's why in your next homework, you will be asked to actually try coding this yourself, and you will be able to see that this is something that can help you find the beta hat parameter estimates once you reach convergence. So nothing fancy, it's just that you're doing this weighted least square iteratively. Okay, so that's the algorithm part. Do we have any questions before we continue? Okay, if there are no more questions, then let's further look into the update, this working dependent variable, to give you more intuition. So what we can say here, well, I will give you two questions to ask. What is ZIK? So just for your information, this Z is a vector. So we can expand it as say Z1K to ZNK, corresponding to Y1 to Yn. And we know that this ZIK, by our definition, is just Xi covariant transpose times beta K plus Yi minus mu I. So by the definition of this, scrolling back here, yi minus mu I, g prime mu I. That's the ith element in this vector. And we have it here. Okay, so it's yi minus mu I, but don't forget mu I should carry the k with it. It's in the kth iteration times g prime at mu I k. Okay. And what we are actually having here is this expansion. Like I said, it can be interpreted as Taylor expansion. And let's first look at, how to say it. We want to look at the definition of linear predictor. So try to give you more intuition and interpretation of this. Recall that eta I is the linear predictor is equal to G mu I, right? This is in the systematic structure. And then eta I itself is Xi transpose beta. Then if we want to do Taylor expansion of eta I around mu I, around the current value of mu I, which is mu ik, then by Taylor expansion, what we can have is eta I minus G at mu I k. Okay, so basically it's G mu I minus, maybe I should just write G mu I. G mu I minus G mu ik. We do the Taylor expansion, first order. It can be approximated by mu I minus mu ik times G prime mu ik. We're doing expansion at around mu ik. And then the left-hand side is just this one. Left-hand side is just eta I, right? Eta I is G mu I. And this is eta I k. And furthermore, don't forget that eta I k is xi transpose beta k, because eta I is the linear predictor. So then with this, you see I have eta I minus xi transpose beta k approximately equal to this. Then together, you see that this will give me eta I as approximately xi transpose beta k plus mu I minus mu ik G prime mu ik. Okay, so if you compare this form to this working dependent variable, what do you see as the similarity and the differences? So they are basically similar, except that on here, the left-hand side, I have eta I. Here I have zik. And on the right-hand side, here I have mu I. Here I have yi. Okay, so basically you are saying that you can see that what I'm doing here is that I replace on the right-hand side, I replace mu I by the random observation. So mu I is expectation of yi. This is expectation of yi. But I replace it by yi. So that on the right-hand side, everything is observed, right? Because mu I is unknown. It's the true value for expectation of y, I don't know it. But I have the current value of beta k, I have the current value of mu ik, and I have the current value of g prime mu ik. So everything else is observed except mu I. So I actually replace mu I by the random version, the observed version yi. Then I call this the working dependent variable. But essentially, you see, what I'm trying to do here is that I'm trying to convert my response, yi and mu I, to this g mu I. I try to work with the link function transform version, so it become linear. Because you know g mu I, which is eta I, is a linear predictor. So I try to turn this non-linear thing into a linear thing via this Taylor expansion. So I'm trying to do this Taylor expansion on the G so that I know this expansion works well when mu I is close to the current value mu ik. So in this neighborhood, it works well. And then in this neighborhood, I do this Taylor expansion to convert my yi to this thing, which I call zik. So then this zik will be approximately linear with my covariance. That's the intuition behind it. I hope you think it makes sense. So the working dependent variable becomes like a linear model scenario. what we try to get out of the link function thing. Okay, that's the first question, how to interpret the working dependent response variable. Second question is, what is WIK, the weight, okay, which is WIK is the inverse. We can just write it. Is the inverse of variance of yi, and this variance should also carry a k because the variance involves parameters and we are using the kth values, the current values, times this g prime mu I k square. So as long as we involve parameter values, we should carry k. And now because you see, this is the form of ZIK. And in this ZIK definition, what is the random variable? Yi. Yi is the only random variable because the xi is fixed, parameters are fixed, so only y is a random variable. So variance of ZIK should be variance of yi times the square of this g prime, which is here. So that's why this is actually 1 over variance of ZIK. Okay, so that's why if you remember when we talk about weighted least square, we said that the weights should be the inverse of the variance of the response variable. The larger the response variable's variance, the smaller the weights, which is exactly here. So you see, once we realize that the weights are actually the variance of the working dependent variable, this confirms that what we have up here is weighted least square. So they perfectly satisfy the requirement for the weighted least square. Each weight for observation I is the inverse of the variance of the response, which is here. And here the response is the ZIK. So basically we confirm that this is the weighted least square with ZK as the response. Okay, any questions so far? Working response variable in the iteration. Each iteration, we need to update the weighted, we need to update the, okay, so coming back here, in each iteration, we need to update the weights and we need to update the working variable, working dependent variable. Then together, we get the next value. So in the following, I will try to give you a detailed description about the iteration. So in each iteration, how do we update parameters and how do we get to the next value? Okay, so if there are no more questions, then let's continue. So the detailed iteration. So first of all, we need to initialize, right? And we need to know the parameters we need. So in initialization, so if we go back to here, we see that in each iteration, if we need to calculate WK, we need the variance of yi, and we need just mu I, right? These are what's needed for W. And in the ZIK, in the Z definition, we need beta, and we need mu, and we need, this is also this d eta d mu. If we go back here, it's basically the G prime mu. So we need mu, we need beta, and we need eta. So these are the things all we need to update. So in the initialization, we set initial values for them. So we set mu 0 just as y, our response. Because mu I is expectation of yi, so it makes sense to set an initialization of mu I as yi. But we have to be we have to be careful. The reason is that, for example, for logistic regression, yi is 0 or 1. But mu I as the probability of taking value 1, it should be between 0 and 1. Otherwise, you have 0 or 1, you have this infinity case, means we take the logit, right? Logit 0 is negative infinity, logit 1 is positive infinity. So you enter that infinity thing. So you may need to add some perturbation to make the mu 0 valid with some perturbation. Or there's a word called jittering. You might have heard this with R plotting. So by adding some small noise so that you add some perturbation to the data. So with this mu 0, then eta 0, we just carry out other parameters based on their relationships. Eta 0 is just G at mu 0. And then Z0, that working dependent variable. So if you recall, coming back here, this is the Z. And don't forget that because of the linear relationship, linear predictor, the first term, this first term can be written just as equal to eta I k, because eta I k is the linear predictor. And we have eta I there already, so we'll use it. So then Z0 is eta 0 plus yi minus mu I 0 yi minus mu I 0 times G prime, derivative of link function at mu I 0. That's the initialization for the working dependent variable. And then Wi 0 is just the inverse of variance of yi 0. So this variance form depends on the specific distribution of yi. So if it's Bernoulli, then it's just mu I times y minus mu I, right? Mu I is the probability. If it's Poisson, then it's just mu I. So for specific distribution, this variance of yi will take different forms about the parameters. And we have this G prime mu I 0 square. That's the weight. Okay, so we have mu 0, eta 0, Z0, the dependent working dependent variable, and the weight. Then we update. The first thing we want to update is the beta parameter value, beta 1, by the weighted least square. It's just X transpose W0. So we will put those WIs into a matrix, right? So this will give me W0 is just W10 to WN0. That's it. So we put it here, X inverse, X transpose W0, Z0. Oh, by the way, I think I should put ZI here. Yeah, I missed the subindex I here because I will use the vector, but this is the scalar. So then this will give me Z0 just as a vector, Z10 to ZN0. All right, this is the beta update. Then correspondingly, we update eta. Eta 1 is X beta 1, linear predictor. And I'm now using the matrix form. And then, furthermore, we need to update mu and zi, right, for the next round. So mu I1 is just the inverse of G applied to eta I1. The reason is that GI1 is G, eta I1 is G of mu I1. So we take the inverse of the link function. And finally, ZI1 is eta I1 plus yi minus mu I1 G prime mu I1. Okay, we update the ZI. Then finally, W I1 is 1 over the variance of yi, which needs update itself depending on the current values, times G prime mu I1 square. Okay, that's how we do the update. So in each update, we will just update the 3 parameters related to the location, which is mu I, eta I, and beta, right? Beta is the common beta. Beta has no I, but eta has an I, mu has an I. And then we update the working response variable, working dependent variable, and we update the weights. And then we do the update in the next round. All right, do we have question? Yeah, there's a hand. Could you ask your question?
Professor, why is variance of yi changing? Do we not have the data set yi?
Why does y variance of yi come in? That's
In
your
wi calculation, like you have variance of yi and there is a superscript 0 and 1. So why
yes,
is
because
variance changing each round?
so what is your last question, last sentence?
Why is the variance changing in each iteration?
Because the variance of yi would involve parameters. And as you update the parameters, you will update the variance. That's the reason. So for example, if yi, let me give you one example. If we have this yi as Bernoulli mu I, because mu I is the mean of yi, then you would have variance of yi as mu I 1 minus mu I. So therefore, if you update your mu I, you will update this variance. Yeah.
Thank you.
Thank you. Okay, thank you for the question. And now let's talk about some specific examples of the logistic regression. I think once we get to concrete examples, it may be clearer. So what we have talked so far is the general form for the iterative weighted least square for exponential family GLM, generalized linear model. Then now we'll talk about logistic regression. Then we will have specific forms for the variance of yi, and we'll have specific forms for the G function, the link function. Okay, so let's look at logistic regression. Okay, and we'll talk about 2 cases. The first case is individual data, if you recall. For individual data, which means that every observation has its own covariance. There's no common covariance shared by multiple observations. And the opposite to this is called group data. For example, if our covariates are categorical, it's very likely that we have some observations share the same covariates, like same age, same gender, same education level. In that case, when we say group data, we just group them together. So for example, if we have 3 people share the same covariates, we just record their total number of voting 1. So like 3, if out of the 3, 2 of them voted 1, then we will count 2. So we'll record 2 as the count. 2 out of a 3 voted 1, instead of recording individual things, because that information is not helpful since these people share the same covariance. So that's the group data, like a data compression. But for individual data, each yi has its own different xi. So in this case, we have yi binary, and their xi is unique. it doesn't share the same covariate vector as other observations. So here the parameters. We have Bernoulli. So basically, mu I is equal to expectation of yi. Mu I is the general notation. But for Bernoulli, if the random structure is assumed to be, if we assume to be Bernoulli with the probability pi I, if we use the pi I notation, then this is also pi I. Pi is more common between 0 and 1. And then the variance of yi is just pi I times 1 minus pi I. Yeah, we already introduced it here. And then the eta I, which is the linear predictor, it takes the g function, it's the logit of pi I. And we know that the definition of the logit function is the log of pi I y minus pi I. And we call this g function of pi I. This is the g function. So therefore, if we need the g prime, the derivative, g prime pi I, we just need to take the derivative of this, and we actually get it 1 over pi I plus 1 over 1 minus pi I. So I skip the calculus detail. Basically, this is the result if we take the derivative. And we can actually show that it can be combined as 1 over pi I, 1 minus pi I. That's the g prime. Okay, then in the kth iteration, so basically in the kth IRLS kth iteration, we want to update these parameters. So suppose that we already have these things. So we already have, let me just say that we have eta ik as the current value, and we have pi ik at the current value. So if that's the case, and then you see that we just need eta I, and mu I, the current value, to update the zi. And here the mu I is just our pi I. So they are the same thing. We use pi I. So therefore, our zik is just eta ik plus yi minus pi ik. Okay, this is it. And then we have the g prime as the gradient, as the derivative, which is here, times 1 over, plug in the current value, pi ik, 1 minus pi ik. That's it. That's the working dependent variable. And then we update the weights. W ik, which is 1 over the variance of yi at the current kth value times that g prime, the gradient, right, derivative at mu k. So g prime mu ik squared. So we just plug in these all things, and mu I is pi I. So it becomes variance pi ik 1 minus pi ik. And this is the g prime 1 over pi ik 1 minus pi ik square. And we can cancel out one copy of pi ik times 1 minus pi ik. So I get 1 over pi ik times 1 minus pi ik. So then I can cancel out the two inverses. So I get pi ik 1 minus pi ik. That's it. So this is the weight. And then with this weight I put them into a diagonal matrix, and I stack the zik into a z vector. Then I can update. This is the key part. Beta k plus 1 becomes just x transpose wk x inverse x transpose wk zk. Okay, coming from up. That's how I update the beta. Once I have the beta updated, I can update all my mean parameters. That is eta, I'll just write the kth one, ith one. Eta I k plus 1 is just xi transpose beta k plus 1. Update eta. And then for pi I k is just the G inverse eta I k plus 1, sorry, k plus 1. And the inverse of the logit function is actually, this is good to know, is the exponential function to the eta I k plus 1 over 1 plus exponential function to the eta I k plus 1. That's it. That's how we do the update for the logistic regression. So we update working dependent variable using current values, parameter values. We update the weight using current parameter values. Then given the two, we update beta using weighted least square. And then given the beta, we update eta, which is the linear predictor. And given the eta, we update the mu I, which is expectation of yi. And here the mu I is just pi I. Okay, so we can update everything. And in the logistic regression, the two key parameters are just eta I and pi. So if you want to remember it, just remember that we need the mean of yi, mu I, and we need the linear predictor. We need those two things, then we can continue doing this update. Okay, so any questions? And of course, for this initialization, we need to make sure that when we initialize pi I, we need to make sure it's not exactly 0 or exactly 1. Otherwise, we will be trapped there. That's the thing we need to remember when we do this numerical optimization for the initialization. So a common suggestion is that if your yi is 0, then you initialize pi I 0 by some value small, but not exactly 0, maybe 0.1. If your yi is 1, then you initialize pi I as a value close to 1, but not exactly 1, maybe 0.9. Okay, any questions before we continue with the group data? Okay, if there are no questions, then let's look at the group data. Also as a very good chance for review. For the group data, we actually have Ni as the number of observations in group I. And we also have each group with its own covariance. So Xi is the covariance shared by group I. So in group I, all the observations have the same Xi. So in this case, we have Yi follows binomial instead of Bernoulli. Binomial, total Ni, probability of success, pi I. So in this case, you know, the mu I, which is expectation of yi, would be equal to Ni times pi I instead of just pi I. So that's why for group data, we need to have this specific consideration. So for the parameters, we have mu I as expectation of yi as Ni pi I. Okay, so you have this Ni thing here. And for the variance of yi, which is what we also need for wi, for the weights, is Ni times pi I 1 minus pi I. And if we want to write it in terms of mu I, it's actually mu I, ni minus mu I divided by ni. The reason is that mu I is ni times pi I. Then eta I, linear predictor, it's still log pi I 1 over pi, still about the success probability. But now we want to write it in terms of mu I because we want a g function to be in the form of mu I instead of pi I. So for individual data, we don't have this problem because mu I is just equal to pi I. But for here, we have this factor ni, and we must consider this. So we can write as log of mu I ni minus mu I. So you see, once we cancel ni from the numerator and denominator is this. And we call this G mu I. Okay, then correspondingly, we can have G prime mu I just as 1 over mu I plus 1 over ni minus mu I. And putting them together, we have ni divided by mu I times ni minus mu I. That's the G prime. Okay, we have everything for our current parameter values, and then the relationship among them. Then we want to update parameters based on the kth, the values in the kth iteration, and we want to get the next update. So similar to what we had before, similar to what we have above, like here. So we will write, I'll just write it correspondingly. We have the IRLS kth iteration. And now we have eta ik and mu ik. Okay, we have these parameters. And then we do the update. So first we update the zik. We calculate, I shouldn't say update, we calculate the work independent variable based on the parameters. So it's eta ik plus yi minus mu I. Okay, the current parameter value for the current expectation value for yi times this gradient, right? Derivative ni mu ik ni minus mu ik. That's the working dependent variable. Then we update the weights. Wik 1 over the variance with the kth parameter values yi g prime mu ik square. Okay, and then we plug in those values. So basically, it's the same idea. Variance of yi is this term. We multiply it by the square of the g prime, which is this term in the denominator. Then we take the inverse. So we can also cancel out one copy when we multiply. Then the end result is, I skip the detail, ni in the denominator, mu ik, ni minus mu ik. That's it. So that's how we get the wik. Okay, then with the working dependent variable zik, with the weight wik, we do the update. Okay, so in the update, similar to what we have for the individual data, we just do the beta. Beta is by the weighted least square. Eta ik is the linear predictor, and then pi ik is the inverse of the link function. So these things all follow. But if I want to write it out once again, just as a to make you sure that you are familiar with this, it's just beta k plus 1 x transpose wk x inverse x trans wk z k, right? Weighted least square. And eta I k plus 1 is xi transpose beta k plus 1. This is it. And finally, we want to update the mu ik, which is the inverse of this. Okay, so similarly, what we want to do is that we will do this inverse eta I k plus 1. Okay, and the good thing is that we can show that it's actually the same thing as what we have here, except the ni. So basically, we need to just make sure that when we solve this, this is no longer 1, but this is ni. That's basically it. Otherwise, it's the same thing. So I will leave this for your calculation. How do we go from eta I k plus 1 to mu k plus 1 to mu k plus 1? We do the update. Okay, that's it. So for group data, we just need to be more careful with this ni involved. And actually, you know what? So people tend to call this ni, give it a name as the offset. You will see this term ni, involvement of ni as the offset in some literature discussion. It's because we need to take care of it. It's not one. It's not one as in the individual data. Okay. That's the logistic regression, and that's about the parameter estimation for beta. Once we get the solution, so ultimately, once we do this, ultimately we will get a beta hat. Okay, the solution, once it converges, beta hat MLE is what we get, the convergence. Of the IRLS algorithm. Any questions?
I was maybe curious what would happen if we just ran the group data and the like individual iterative method. Like, would the betas be quite different?
Oh, very good question. If you run the group data as individual data, as long as you keep your yi as 0, 1, you just separate each group into, say, ni observations, right? Previously, you just have one entry for this group I, but now you separate this entry into ni entries for ni observations. You can do that, and the results should be identical.
I see. Okay, thank you.
It should be identical. It's just that if you do it this way, it saves your computer memory, right? You're not saving so many entries. Yeah.
Okay, gotcha.
Yeah. Good question. Okay, so now let's talk about once we have this, like in our linear model, we want to do model assessment. How do we assess whether the model fits well to the data or this is a good model? So next question is that we want to do goodness of fit statistics. This is the strength of statistical analysis. So when we have a model, we want to assess how well the model fits the data or whether the model is reasonable instead of just saying, okay, we're happy with the beta hat as our estimate and we continue from there. And as opposed to machine learning is more interested in just estimating the parameters and then do the prediction. So the key difference in the thinking is that if we want to use the beta hat for inference of beta, we need to make sure that it's reasonable. So I think the question is whether our interest is more about the model or more about prediction. So if the interest is in the prediction as in machine learning, then how to interpret the beta is not as important as long as the prediction accuracy on your test data is good enough. So this is actually what's happening in the deep learning community. We know that there could be multiple ways or multiple sets of parameter values that lead to similar prediction performance. But We would be happy as long as the prediction is good for tasks where interpretation is not so important for our model, such as image classification or such as text classification. We don't really care what's going on in the model because the decision is not a high stake. Even though we make some mistake, then we can tell by human correction. We're not so concerned. But if our concern or if our focus is on the model, we want to tell a story out of the model, like in social science. How much does education level change our income? If you want to answer that question, then your focus is on your model. So therefore, the model parameter inference is your goal. And therefore, you want to justify this is a reasonable model. Otherwise, how can you trust the story you told from the model parameters? So that's why it's a different perspective. I hope that this is something you can be more aware of after this class. So for the goodness of fit statistic, so one thing we actually use as a how to say, as a counterpart to our mean squared error, or the, yeah, I should say mean squared error for the linear model is what we called deviance. So this is a term I want everybody to be familiar with after this class. Deviance is just the mean squared error for linear model, or I should say not the mean square, the residual sum square. Yeah, residual sum square for, it's just like the RSS, or we also wrote as SSE, right? Sum of square error, residual sum square. You see both for linear model. For linear model, the deviance is the counterpart for generalized linear model. So what is the deviance exactly? It is basically the likelihood ratio test statistic to compare two models. Of the generalized linear model you fit using the covariance versus the saturated model. Saturated model is what we have seen already for linear regression. That is, you predict you estimate mu I just as yi. So mu I hat is set to yi. So in the generalized linear model, you have this assumption that G mu I is xi transpose beta. So you see, this is called information borrowing from your observations across your n observations, because even though your n observations have different xi's, they share the common beta. And this common beta determines their different mu i's. So their mu i's are tied together by this common beta. But in the saturated model, you don't have this information sharing to tie your mu1 to mu_n together. You keep them as separate parameters, mu1 to mu_n. That's the difference. Okay, so therefore you have how many parameters? N parameters. While over here you have only p parameters. P parameters. And this is n parameters. And in the statistical setting, if we want to learn parameters, we want to say something about parameters. Your number of parameters cannot be more than your observations. You cannot afford that. But in the deep learning, it's a totally different world. People can have, how to say, for ChatGPT, how many parameters you have? I think ChatGPT 3 has about 100 something billion parameters. And then for GPT-4, you have 1 trillion parameters. So the parameters, they are not for interpretation. They're just a engineering tool, right? You try to use it for your own task, but the model itself is not something you want to understand. That's a very different thing. But here, you want to understand the parameters, and you cannot have more parameters than your observations. Otherwise, the parameters will have different sets of values that will give you the same fit. You can fit a saturated model. So that doesn't make sense. So if you want to interpret the parameters, you want the parameter estimates to be unique. That's in statistics what we call identifiability. You want to just have one set of parameters that give you this likelihood value. Okay, what is the deviance statistic then? what is the likelihood ratio test statistic, if you remember? It's the -2 times the log ratio, log of the ratio. And in the ratio, you have the simpler model in the numerator, simpler models likelihood in the numerator, and you have the more complex models likelihood in the denominator. So therefore, the ratio is less than 1, log of the ratio is negative, and -2 times the log ratio is positive. So that's how the story flows. And then this -2 log ratio, log likelihood ratio, if the bigger, it means that the more different the two likelihoods are, then the more different the two models are. So therefore, we prefer to have a smaller likelihood ratio statistic, which means that the likelihood based on the GLM is not so much smaller than the likelihood based on saturated model. Then it means that our model, our GLM, fits well to our data. That's the rationale. Okay, so then specific deviance statistic, short written as D, is defined as the -2 times the log of this ratio. So the first one is the maximum likelihood of GLM over the maximum likelihood of the saturated model. Saturated model. So that's how we do this two things. And then you know that I can make this log of likelihood ratio as the differences of two log likelihoods. And because of negative sign, I can change the order. So it becomes 2 times the log likelihood of the mu parameter vector, which is n-dimensional, estimated under the saturated model, minus the log likelihood of the mu estimated under the GLM. That's the deviance. Okay. And then when we write down the log likelihood, we need to rely on the specific distribution of yi, right? So if like the yi, for example, for group data, let me just give you that example. If the yi's are independent binomial ni pi I. Okay, how do we write down the likelihood? And we can actually do it this way. So basically, I'll just quickly write it down before we wrap up. So the likelihood of mu is basically the product, right, from 1 to n, the probability mass function, f, I just wrote f at yi, the observed yi. And then we will use the probability mass function from binomial. Just for your information, this is actually equal to pi I to the power ni times 1 minus pi I to the power yi, sorry, yi ni minus yi. That's it. Okay, I'm not using mu I yet, but I can later convert pi I to mu I. So then if you take the log likelihood of mu, you just take the log of the whole thing and product becomes sum. And the power will come down as polynomial. So then you would have the summation, you have yi times log pi I, right? Plus ni minus yi log 1 minus pi I. Okay. And finally, if you want to introduce the, how to say, if you want to introduce the mu I, if you want to introduce the mu I, then you use the relationship that pi I equals mu I over ni. Then you just replace everything inside as the mu I. And basically you can easily see that you would drop this constant term just involving ni because they're not involved. Maybe I just write it. Yeah, I'm just talking. So you have yi Okay, log mu I minus log ni. That's the first term. And ni minus yi. So this can be written as log ni minus mu I minus log ni. Okay, and as we are only concerned about the terms involving mu I for the log likelihood, because we want to maximize the log likelihood in terms of mu I. So anything not related to mu I can be gone. So you can actually see that it's basically a summation I from 1 to n, yi log mu I plus ni minus yi log ni minus mu I plus some constant not involving mu I. That's it. So when we want to maximize the log likelihood, we just want to maximize the first term. Okay, so this is the deviance statistic. As long as we can write down the log likelihood for the two mu parameter estimates, one under the GLM, one under the saturated model. And under the saturated model, each mu I hat is just equal to yi. We said it in that way. So that's what we have here. So next time we will come back to talk about the deviance test statistic. And also we will give you another goodness of fit test statistic. Goodness of fit test statistic called Pearson chi-square statistic, which was independent proposed in history. And then from that, we can use either of them to assess how well the GLM model fits to data compared to the saturated model. That's about the model fitting part. And then regarding the inference of data, next time we'll also talk about how do we use the MLE, beta hat MLE, as a way to construct a test statistic. Then we can test beta to see whether beta is 0 or not. So that's the plan for our next class. All right, so that's all for today. And I'll see you on Zoom again on Wednesday. And I hope everybody stays safe. And I'll stay in the Zoom for a while in case you have any questions.